So hello and welcome back to part 2 of Lab 1 Recitation on Let's Get Moving, Getting to Know Your Robot. Today we're going to focus on the proper way to comment and create your code, on making a software design plan, as well as giving a little bit more detail about feedback control with respect to encoders in order to correct for odometry error. Please come along. So a big part of writing code is program design. You're going to be required to make a software design plan for the code that you write in this course. Before you write any code, it's very helpful to make a design. Why is this important? Because a little extra time spent in the design process can save a lot of time in implementation, in troubleshooting, and debugging. It also helps with the divide and conquer approach to development, such as by making this flow chart or pseudocode or state diagram or subsumption architecture. You and your lab partner can now divide and bring things back together by having a common goal and understanding the common approach for variables, functions, etc. So in part of the systematic code implementation process, you want to organize and plan out your code before you actually write your code. You want to use a systematic approach to the logic to understanding where functions do you need, what variables do you need, and also you want to comment your code as you go. Let your lab partner help in that process if it's their week to write up the memo while you're doing the programming. The different kinds of ways we would do software design plans in this course include pseudocode, flowcharts, state diagrams, and subsumption architecture. Sometimes I will tell you which one to create. Sometimes it'll be your choice. By the time we get to the final project, you have to have a software design plan, but I will let you select which one you want to do. Remember, in pseudocode, an algorithm is a procedure for solving a problem in terms of actions to be executed. And the pseudocode is an artificial and informal language that helps programmers develop those algorithms. It's informal, natural language. So you're not writing out code. Pseudocode is actually normally written in natural language. For example, here is a stopwatch that has 3 states: reset, run, and stop. So you initialize the counter to 0, the reset to 1, and the run to 0. Then you're going to have an if function. Is the button pressed? Based upon the decision, if it's no, stay in the current state, reset. If it's yes, then you want to increment the counter and set reset to 0 and set run to 1. It will continue to increment until the button is pressed. If it's pressed again, you save the final counter, reset still 0, run to 0. If it's not, you stay in the current state, run. And if you press the button a third time, then yes, return to reset. If no, you stay in the current state, which is stop. Notice there is no formal language, coding language here, but it gives you all the logic you need to write the code. So next, let's talk a little bit about the Excel stepper library. Along with the step stick, this is the library you're going to use in order to move the motors on your robot. So to understand more about the library, you should review the documentation, run several of the examples that I have created along with the ones that come with the library, in order to understand what it means to be blocking, bouncing, constant speed, multi-steppers, overshoot proportional control, quick stop, or the random functions inside of the library. So here are a few more helpful hints along with the ones I've already given you to help you to be successful at Lab 1. Confirm that the wiring on the robot matches the code. This is a common mistake students have where they'll tell me something's wrong with the robot when it turns out the wires do not match the wiring on the code. Understand which functions in the library are blocking and understand what blocking means. Run, acceleration, deceleration, does not block. Run speed, which has a constant speed, does not block. And run to position, which has acceleration and deceleration, does block. And run speed to position has a constant speed and it blocks. And run to new position has acceleration and deceleration and it also blocks. Most importantly is that if you are running a function that is blocking until it finishes all the steps or all the movements or gets to that final position, it hangs up the code and nothing else will run. Also remember that run to stop, the function, is used to increment steps when the motor has steps left. So it will continue to run until it has moved all of the steps. Also set max speed and set speed. Some functions in the library reset the speed to 0. Depending upon the function, either set speed or set max speed will be required in order to vary the motor speed. If you're finding it's not working, it's probably because the function in the library is resetting the speed when you call it. There are two different ways that you can implement two speeds on the wheels, which will help you with the turn function and with the circle function. One of them is to use stepper right dot move and stepper left dot move and put in two different positions, put it in two different accelerations and two different speeds, and then run speed to position. Another way to implement turn or circle is to set two different positions like 1200 and 800, set two different speeds, and then use run to and run speed to position. There are more ways to do this. Here are just two examples. Use the library and the sample code to figure out other methods to do this. So recall that for the circle and the figure 8, you don't have to use the encoders, but for go to angle, go to goal, and the square, you need to use the wheel encoders for feedback in order to correct for odometry error. A wheel encoder is attached to the shaft of a motor that drives the robot, tracks and uses black to white transitions or pulses to sense the robot's rotations. So the relative position estimation is dependent on the measurement of the robot's velocity. So these optical encoders can be used on each wheel to measure the angular position and or velocity. If the robot moves straight ahead, you can count encoder pulses to determine its new location. You should do this. Measure the diameter of your robot, determine the circumference, figure out how many encoder pulses are related to a distance. For example, if 10 encoder pulses equal 13 centimeters, then the encoders will have an error of 1.3 centimeters. This can be serious for short distances, and accumulated error can also cause problems. By using this math, if we have wheel circumference divided by 16 pulses, then we get 1.3 centimeters by having 6.62 centimeters pi over 16. So now what if we want to use encoders to measure spin angle, like in go to angle? So assume that the robot turns around its center, so spin, where V1 equals negative V2. If the robot has a diameter of 10.8 centimeters, the circumference pi d is pi 10.8 or 33.93 centimeters. So if each encoder pulse indicates a travel distance of 1.3 centimeters, then 1.3 centimeters divided by 33.93 centimeters times 360 degrees means that every encoder pulse, the robot rotates 13.79 degrees. You can now use this along with your commands to estimate how far the robot turns based upon encoder pulses, or you can use stepper commands and then use the feedback from the encoders to correct for turning error or angles as part of that odometry error. What about using encoders to measure turn angle? So when the wheel velocities are not equal, the robot will now turn or move in a circle. So each wheel will trace out a circle with a different circumference. The diameter of the robot, let's say, is 10.8 centimeters. The length of the inner arc is S2, or R in inches theta. The length of the outer arc, or the right wheel, will be S1, which is Rn plus L times theta, or S2 plus L times theta. So the angle theta would be S1 minus S2 divided by L. So the length of the arcs can be described in terms of the encoder pulses for the right P1 and left P2 wheels. Remember, we said when we're tracing out our circles, we typically try to use the center of the robot, which would now be the average between that inner and outer diameter. So the difference between the encoder pulses, P delta, which is P1 minus P2, you use this to find the change in the angle, where theta delta is equal to P delta times 1.3 centimeters per pulse divided by 10.8 centimeters, or 0.12037 P delta radians, which translates to 6.897 P delta degrees. So note that when the pulses of both wheels are equal, i.e. the same velocity, then theta delta would be equal to 6.897 P delta degrees, or 13.79 P1 degrees. So to find the XY position of the robot, substitute encoder pulses for velocities in the forward kinematics equation. And now you can use the encoders for the movement instead of just commanding the steps or velocity, etc. So here's what this looks like in terms of feedback control, where your output instead of velocity would be steps. But you would input the X, Y, and theta for the pose. Then you would have the controller that is minimizing the error, where the error is the feedback from the encoder, that's now dictating the velocity and the angular velocity in order to get the robot to move to a certain pose in the world, or an X and Y position and orientation theta. So the first way you could do this is with PID control, where if you have Kp times I plus Kd times di dt plus Kf times the integral of I, where I is the error input in terms of the value, the change in the error, or the accumulated or the integral of the error. So let's say we start with just proportional control. In order to control rotational position of the robot, you would pulse steps at a given speed. So if you want the position to be 100 encoder pulses, the controller will vary power based upon the error between the current number of encoder pulses and 100 pulses, where the encoder will now keep track of the shaft position as well as how many pulses have currently been executed. So then what happens with a simple proportional controller is the command is 100 minus encoder counts. The initial error is 100, so the motor would turn up 100% of full speed, and then as the error becomes progressively smaller, the motor power will then become proportionally smaller based upon that error. So if I'm at 50, the motor power will now be at 50% of full power because I'm only 50 encoder counts, and then when it gets to an error of 0, then it would just turn off. This is an example of proportional control, where in this example, the gain is just 1. If the gain is a 5 instead of a 1, now the motor will be more aggressive and there will be more resistance to turning away once it gets to the set point, and it will reach the set point quicker. And this system will now be an example of critically damped, which you learned about in your feedback control course. So what does this look like graphically? If our proportional gain was a 10, what you will see is that as the encoder counts get closer to 0, there will be a slight amount of overshoot here, where the offset error may not reach the final value because there may not be enough of a gain in order to get rid of that error, but there will be some overshoot, and the system never does stabilize completely at the goal, and the power command is too small to activate it. So you then turn up the gain, and now you're going to get more overshoot, but the offset error has been solved, but there now is going to be some oscillation because the system now overshoots 3 times before it reaches that final value. So as you continue to turn up the gain, what you will notice is that the system will become underdamped and the oscillations will become more increased. And eventually, if you turn the gain up high enough, it will yield an undamped or marginally stable system where it will never reach the error. It will never get the error to 0. It will never get to the final value. And that small error will never generate enough power to move the system back to the set point. So that means continuing to increase the proportional control is not going to fix the problem. You have to have a different solution. That different solution is derivative control. So setting gains can be difficult, and simply increasing the proportional gain we now know does not work because it makes more increasing oscillations and eventually an unstable system. So what you want to do is to add derivative control. The benefit of derivative control is that it is rate control, and so it adjusts for the rate or the quickly changing error in order to correct for that. So it basically puts brakes on the system or slams on the brakes so that when the momentum, which equals mass times velocity, becomes large, it will slow down on those oscillations. So it does this by correcting the momentum as the system approaches the desired state in order to make it to still correct to 0. This is called the derivative term for a PID controller because it's a velocity is the derivative of the position or the derivative or rate of change of the error. So now you're controlling the velocity with the derivative control because the momentum and the derivative controller are related. So now you're going to have KD times the derivative of the error. Note that in a microcontroller, it's not actually derivative, it's delta error. So what you're going to do is use the previous error and the current error, and you're going to use the difference between those two values multiplied times the proportionality constant in order to influence the motor or the turn speed or turn angle, etc. So based upon the derivative control, the controller is going to correct for the momentum as it approaches the desired state. So it slams on the brakes to stop the oscillations. It slows down the robot and decreases the turning angle while getting closer to the desired state, and it decreases the motor power while getting closer to the desired state as well. So now integrating that with the proportional gain to make a KP or PD controller. So you're going to have KP times the error input plus KD times the derivative. And based upon how you have written your program, you may be subtracting off the KD term. So PD control is used extensively in industrial process control because it's a combination of varying the power input and the derivative in order to yield the result that you want. So here's an example where the proportional gain is 4, the derivative gain is a 1, and now you see that the oscillations are reduced. There is no steady state error, and it does get to the final value. Overshoot is minimized, and there's no oscillation behavior at all. So now let's see what happens if you change the gain to 10 and the derivative to 5. Turning those gains up, you now have brought the oscillations back because the derivative gain is too large. And so now you slam on the brakes too quickly, and it does not get to the final value, and it actually has a steady state error between the 0.8 and 1 second remark. But when the velocity hits 0, the proportional gain kicks in again, and the system corrects. Now, for integral control, this is when you have a steady state error. So the error accumulates as the robot is running over a long time. And in a microcontroller programming, integral control is actually a summation. So what you're going to do to solve the problem is you sum up the error over time. And after the error exceeds a given threshold, then the integral controller should kick in to try to reduce that error to 0. So once that becomes large enough, the robot will then make an adjustment with motor speed or with a turn angle to try to reduce that. So Ki times the integral of the error. And remember, this is a summation in your microcontroller code. So the intuition here is that the system has to keep track of its repeatable steady state errors over time. It has to add them up, and then it has to determine that threshold and then use the system to compensate for them. So now let's finish up the Lab 1 recitation with a couple of quick reminders. The first one is about wiring peripherals and sensors to your now gigabyte. Even though this video was made for the megabyte, everything still stands for the gigabyte other than your sensor rail is 3.3 volts instead of 5 volts.
So when you get your robot, there may not be everything wired up on it. So you're going to have to do that and try to do it a little bit neater than what I did here. But the first thing I want you to note is that you should only use this front bus, voltage and ground, for your sensors. It's 5 volts. This back bus, you can use the ground because the grounds are tied together, but do not use the red line, the voltage line. That's 7.2 volts. That's for powering the motors and the board when it's not tethered to your laptop. Also notice that you have this switch here. When the switch is forward means you're only powering the 5 volts, which is everything but the motors. So if you want to test out your sensors, your LEDs, have this forward. When you flip it back, you engage your motors. We've already talked about when you engage your motors, you need to have your robot on the floor or on a test stand so that you don't drive it off the table. You can ignore the camera. Your robot does not have the camera on it. The other thing I want you to notice is you're going to have to wire up 3 LEDs, red, yellow, green, in series with 220, 330, or 100 ohm resistors that should go to ground. And the short leg and the lip of the cap is flat, should be the one to go to ground. The longer leg should then go to pins 5, 6, and 7 on the Mega. 5 is red, green is pin 7, and the yellow LED is pin 6. Then you're probably going to also have to wire up the Bluetooth, right? And the wires for doing that are in your lab, the pin out for that, and your IMU, okay? So remember, nothing gets wired to the red line in the back. That's 7.2 volts. It'll fry your electronics. So use the voltage in the front.
Final reminders. For your demonstration, there's going to be 2 phases. For the first phase of the demonstration, that's going to be due next class, you're already halfway there with the code I've given you. I've given you code that moves your robot. You just have to put that code into functions to implement forward, reverse, spin, left, spin right, turn left, turn right, pivot left, pin right, and stop. And basically what you're going to do is write one loop that calls each function with a delay in between, similar to the video you watched, and check all those off in the next class. Then you're going to spin the remainder of the next class and into the one next week, getting circle, figure eight, square, go to angle, and go to goal, working as well as possible considering odometry error and by using encoder feedback. I will be making you more videos later to show you some examples of how to at least get started doing that. And you also need to have your software design plan to be checked off and reviewed for the next class. Code requirements. All code must have a heading with the name of the file, the name of the team, description of what it does, description of the main functions, name of the authors, date of revision, then single line and block comments as necessary. After all demos are completed on a lab that next Sunday night, the memo with the code in the appendix is due to be uploaded to Gradescope. If you want to see examples of code that has an appropriate level of comments, look at all the sample code that I give you. I actually over comment the code I give you because it's more of a learning tool than just code to get the robot working. But remember, your code must be modular with functions called from the loop function as necessary. No magic numbers, but constants and variables to represent what those numbers are. And code must use defines or constants as necessary. Note that those will be the variable. They're not variables, they're constants because they don't change at runtime. Use header comments as necessary, including at the beginning of functions, loops, etc. And remove any code that is no longer relevant to the lab, and remove any comments that are no longer relevant to the lab. So anything I put in there for you to help you understand the code, take it out, make the code your own, and make sure that it reads like a story so that even if I don't know anything about programming, I could walk through your comments to understand what your code is doing. Remember, inline comments are comments that help with things such as functions, while loops, for loops, if conditions, switch conditions, etc. Always think about if someone's reading your code, would they understand what you're doing and how to implement this on their own? So make sure, once again, you have global and local variables, constants. Function should have logical names. The function should describe what it does. Function 1 is not a good name. Code variable is not a good name. Make sure variable names, function names are very instructive as to what they're doing. Here are examples of ways to eliminate magic numbers from your code, where you use pound defines for each variable, so that if I was wiring up an LCD, I now know that DB6 goes to pin 3, DB7 goes to pin 2. I know that my LCD has 2 rows and 16 columns, etc. I know I have a buzzer on pin 6. I have a red LED on pin 8. I have a temperature sensor on A0. I have a photoresistor on A1 and a button on pin 7, etc. Here are some more examples of a header comment, a function comment, a function call comment, a block comment, as well as inline comments. Make sure you're commenting your code as you go, and that could be something that your lab partner helps with. If you're trading off who's programming and who's writing one week, have your lab partner do some of the coding while you're working on one of the other parts and the commenting. Here are a few more examples where I now have a header name, the author, the date it was created, a description of what the program does, a list of variables and functions, function prototypes, and what they do. I have an inline comment here, a function block comment. And don't forget, code needs to always be named after the robot team name and what lab it is, okay? No code that just says main or lab 1, because I will have 15 lab 1s. Okay, commented as necessary with header comments etc. Always modify the code to meet lab requirements and delete anything from previous weeks that you are no longer using if you're going to keep recycling your code. Use Arduino websites and Google as your best friend for getting help on the Giga, Arduino programming, etc. Don't forget, Pre-Lab 1 is due the next class, and that is your pseudocode written in Word or Google Doc, whatever document you like. It's going to be uploaded to Gradescope, where you write pseudocode on how to use go to angle, go to goal, move square, move circle, move figure 8. Remember, other than circle and figure 8, I expect to see some kind of encoder feedback for odometry correction in your pseudocode. Pre-Lab 1 is due at the beginning of the next class. Lab 1, the move functions are due next class, and then these 5 functions that you're writing the pseudocode for are due 1 week from the lab recitation, which would be today.